Welcome, weary traveler. Welcome to Science for Sleep. Tonight, you have nowhere to be, nothing to do but rest. Let the tension dissolve from your shoulders like morning mist under sunlight. Let your breathing slow, your thoughts soften, your body remember the art of stillness. We're about to drift through 150 quiet truths about the Milky Way, whispered facts, cosmic secrets, gentle revelations. You don't need to remember them all. You don't need to hear every word. These truths are here simply to carry you, like a current carrying a leaf gently downstream into sleep. If these peaceful explorations help you find rest, consider liking, subscribing, or sharing with another soul who struggles to quiet their mind. But for now, let everything fall away. Close your eyes if you wish, settle deeper, and let the galaxy sing you to sleep. Let's begin. Ancient stars, foreign orbits. Some stars in the Milky Way are older than the Milky Way itself. Born in smaller galaxies that merged with ours billions of years ago, they carry memories of other worlds. These ancient halo stars orbit in strange, tilted paths. They move high above and below the galactic plane, on orbits that speak of disrupted origins, of galaxies long destroyed. Their chemical composition is nearly pure hydrogen and helium, almost no heavy elements. They formed before the universe had created much iron, carbon, oxygen, before generations of supernovae enriched the cosmic gas. By studying these ancient stars, astronomers peer into the primordial past, into an era before structure, before spirals, when galaxies were just beginning to take shape. Some stars orbit the galaxy backward. While most stars move in one general direction, these retrograde stars orbit against the flow, swimming upstream. They're immigrants from absorbed galaxies, and their reversed motion is their signature. The Milky Way likely consumed a large galaxy called Gaia Enceladus about 10 billion years ago. This collision added countless stars and may have fundamentally reshaped our galaxy's early structure. Evidence of ancient mergers is written in stellar streams, long ribbons of stars that wrap around the galaxy, remnants of dwarf galaxies torn apart by tidal forces, their stars smeared across space like paint. Some of these streams are so old they've wrapped around the galaxy multiple times, creating complex, overlapping patterns that astronomers are only now beginning to map. The chemical fingerprints of stars reveal their origins. By analyzing the elements in a star's atmosphere, scientists can determine where and when it formed, whether it was born here or adopted from elsewhere. The Milky Way is not a pristine object. It's a mosaic, a patchwork quilt stitched from many smaller pieces, each with its own history, its own story written in starlight. Our place in the spiral. Earth sits about 26,000 light-years from the galactic center, far enough to avoid the radiation, the black hole's hunger, the chaos of the crowded core, close enough to orbit steadily in its gravitational embrace. We live in what's called the Orion Spur, a minor arm between two major spiral structures, the Sagittarius arm and the Perseus arm. It's not the grand boulevard of the galaxy. It's a quiet side street, and that quietness may have made all the difference for life. The solar system orbits the galactic center at 828,000 kilometers per hour, fast enough to circle Earth in less than 3 minutes. Yet we feel nothing. We drift through space in perfect silence. Despite this incredible speed, completing one full orbit takes 225 million years. This vast cycle is called a galactic year, a timescale so immense it dwarfs human history, dwarfs recorded civilization, dwarfs the entire existence of our species. Since Earth formed 4.5 billion years ago, our world has circled the galaxy only about 20 times, 20 laps around an immense cosmic racetrack. We are young. We are so very young. When dinosaurs walked the Earth 200 million years ago, the solar system was in a completely different part of the galaxy. Different stars overhead, different cosmic neighborhood. The sky they knew was not the sky we see. The stars visible tonight are not permanent neighbors. They drift past us on their own orbits, their own trajectories. What seems eternal from our brief perspective is actually temporary, fleeting, always changing. Our sun is a third-generation star. It formed from gas clouds enriched by earlier stars, stars that lived, fused elements in their cores, exploded, and scattered those elements into space. We are descendants of stellar death. The iron in your blood, the calcium in your bones, the oxygen in every breath, all of it was forged inside ancient stars that died before the sun was born. You are made of stardust, not metaphorically, literally. The Milky Way is our home, but we see it from within. We cannot step outside to view its beauty from afar. We piece together its structure like blind cartographers mapping a cathedral by touch, by sound, by inference and mathematics and hope. The ancient river of light. The Milky Way is over 13 billion years old. It was born in the cosmic dawn, when the universe was still young and wild, still learning how to weave hydrogen into stars, stars into galaxies, galaxies into the tapestry we see tonight. Our galaxy contains somewhere between 200 and 400 billion stars. The exact number remains unknown, perhaps unknowable. We are surrounded by more suns than grains of sand on all Earth's beaches, more lights than we could count in 1,000 lifetimes. The Milky Way is what astronomers call a barred spiral galaxy. Not a perfect pinwheel, but something more organic, more alive. A glowing bar of stars crosses its heart, and from that bar, spiral arms curve outward like water flowing from a fountain. From edge to edge, the Milky Way spans roughly 100,000 light-years. To cross it, even traveling at the speed of light, 300,000 kilometers every second, would take 100,000 years. It is vast beyond human comprehension. We call it the Milky Way because of how it appears from Earth. A pale band of light stretches across the night sky, a river of stars, so distant they blur into luminous fog. Ancient Greeks thought it was milk spilled from Hera's breast. Other cultures saw it as a path for souls, a celestial river, a bridge between worlds. The Milky Way weighs approximately 1.5 trillion times the mass of our sun, but most of this mass is invisible. Hidden in dark matter, mysterious, unseeable, yet holding everything together through gravity alone. Every star you can see with your naked eye belongs to the Milky Way. When you look up at night, you're looking at your neighbors. The distant galaxies beyond are too faint, too far for eyes alone to find. The Milky Way is not standing still. It moves through space at roughly 600 kilometers per second, pulled by gravity from distant galaxy clusters, carried by the expansion of the universe itself, drifting through the cosmic ocean. Our galaxy belongs to something called the Laniakea supercluster, a vast structure containing over 100,000 galaxies, all flowing together through space like birds in migration, following invisible currents we're only beginning to understand. The oldest stars in the Milky Way formed over 13 billion years ago. They are nearly as old as the universe itself. Ancient lights that have burned since before Earth existed, before the sun was born, before almost anything we know came to be. The growing galaxy. The Milky Way is still growing. Even now, at 13 billion years old, it continues to accumulate mass. Gas from the intergalactic medium, stars from captured dwarf galaxies, streams of dark matter feeding the halo. This growth is not like biological growth. The galaxy doesn't age or mature, it simply deepens, accumulating matter like snow accumulating on a mountainside over winter. Some growth happens quietly. Cold gas slips into the disk from outside, settling gently into orbit, eventually condensing into new stars. Other times, growth is violent. Dwarf galaxies crash in, their stars scattered, their gas heated and disrupted before settling into the larger structure. The Milky Way of today is not the same galaxy that existed when dinosaurs roamed. It has absorbed satellites, gained mass, shifted shape. It is different now than it was then. And the galaxy your distant descendants might know, if humans survive that long, will be different still. Larger, perhaps, merged with Andromeda, transformed by billions of years of slow accumulation. Two small galaxies called the Magellanic Clouds orbit the Milky Way. Visible from Earth's southern hemisphere, they look like detached pieces of the Milky Way itself, glowing clouds separated from the main river. Recent evidence suggests they may be on their first close pass, not ancient satellites, but newcomers only recently captured by our gravity, first-time visitors falling into orbit. Behind the Magellanic Clouds trails a vast stream of hydrogen gas. The Magellanic Stream, torn from the galaxies by tidal forces, stretches across hundreds of thousands of light years. This gas will eventually be incorporated into the Milky Way, recycled into new stars. The Magellanic Clouds themselves may one day be fully absorbed, their stars added to our halo, their identity erased. The speed of stars. The solar system moves at 828,000 kilometers per hour around the galactic center. Yet in space, there is no wind on your face, no sense of motion, only silence and stars. Different stars orbit at different speeds. Inner stars race around the core in just a few million years. Outer stars drift slowly, taking hundreds of millions of years to complete one loop. This difference in speed creates the spiral arms. They're not solid structures, but density waves, patterns that ripple through the disk like traffic jams, compressing gas and triggering star formation as they pass. Our sun moves in and out of spiral arms over time. Sometimes we're within an arm's dense, star-forming regions. Other times, like now, we drift between arms in quieter space. The fastest stars in the galaxy are called hypervelocity stars. Flung outward by gravitational slingshots, they travel at over 1,000,000 kilometers per hour, fast enough to escape the Milky Way entirely. Some hypervelocity stars were ejected by the supermassive black hole at the galaxy's center. Binary star systems that ventured too close. One star was captured, the other flung away at incredible speed. These rogue stars will travel alone through intergalactic space forever, tiny lighthouses drifting through the void, carrying the galaxy's memory outward into darkness. The sun doesn't follow a perfectly flat orbit. It bobs up and down through the galactic plane like a cork on gentle waves, rising and falling over tens of millions of years. This vertical oscillation is caused by gravitational tugs from the galaxy's mass. As we pass through the plane, gravity pulls us back. We swing like a pendulum, forever crossing the midpoint, but never stopping. Some scientists have wondered whether this oscillation might influence life on Earth. Crossing the dense galactic plane could increase comet impacts or cosmic ray exposure. But the evidence remains uncertain, the connection unclear.
Mysteries of structure. We don't know exactly how many spiral arms the Milky Way has. It seems like something we should know about our own galaxy. But from inside the disk, surrounded by dust, it's difficult to see. For decades, astronomers thought there were 4 major arms. More recent observations suggest maybe 2, or that the arms split and fragment in complex ways we're still trying to understand. Some arms fade into fragments, others wrap around unexpectedly. The structure is not clean or simple, but organic, shaped by gravity and time into patterns we're only beginning to map. The spiral arms are not made of fixed stars, they're density waves, regions where stars and gas temporarily crowd together, like cars bunching in traffic before spreading out again. As gas clouds pass through these density waves, they're compressed. This compression triggers gravitational collapse. New stars ignite. The arms light up with young blue stars born from the squeeze. Eventually, these stars drift out of the arm. The brightness fades, but new stars form behind them, maintaining the pattern. The arms persist not through fixed structure, but through continuous replacement. This is why spiral arms can rotate at different speeds than the stars themselves. The pattern moves through the stars like a wave moving through water. The wave moves, but the water itself just bobs up and down. From far away, the Milky Way would look like an elegant spiral. From within, we see only fragments, pieces of the pattern. We infer the whole from glimpses and mathematics. The galactic disk is not perfectly flat. It warps, bending upward on one side and downward on the other, like a spinning plate knocked slightly off balance. This warp is most pronounced in the outer regions. The disk ripples, undulates, shaped by gravitational tugs from satellite galaxies or clumps of dark matter below.
The hidden majority. Only about 15% of the galaxy's mass is visible. The rest is dark matter, invisible, mysterious, detectable only through its gravitational effects. We know dark matter exists because the galaxy spins too fast. Based on visible matter alone, stars in the outer regions should be flung into space, but they're not. Something invisible holds them in place. Dark matter doesn't interact with light. It doesn't shine, doesn't reflect, doesn't absorb. It passes through ordinary matter like a ghost passing through walls. But it has mass, and mass creates gravity, and gravity shapes everything. The orbits of stars, the structure of galaxies, the formation of cosmic webs connecting galaxy clusters. The Milky Way is surrounded by an enormous dark matter halo. This halo extends far beyond the visible disk, outweighing all the stars and gas combined. We don't know what dark matter is. The leading theory suggests exotic subatomic particles that barely interact with normal matter, but decades of searching have found nothing conclusive. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for a single dark matter particle to collide with an atom. So far, silence. Whatever dark matter is, it's the dominant form of matter in the universe. Everything we can see, all stars, planets, gas, dust, makes up less than 5% of the cosmos. The universe is stranger than we imagined. Most of it invisible, most of it unknown. We live on a thin foam of visible matter floating on an ocean of darkness. This should be humbling, cosmically humbling. Everything humans have ever seen, ever touched, ever known is a tiny minority. The universe is mostly something else. The galactic heart. At the very center of the Milky Way lies a supermassive black hole. Sagittarius A star, it's called. 4 million times the mass of the Sun compressed into a point smaller than Mercury's orbit. We cannot see the black hole directly. By definition, it emits no light. But we've watched stars orbit it at tremendous speeds, tracing elliptical paths around invisible mass. Some of these stars complete an orbit in just 16 years. They move so fast, so close to the event horizon, that their motion alone proves the black hole exists. Occasionally, gas and dust fall toward Sagittarius A star. As material spirals inward, friction heats it to millions of degrees. It glows with X-rays before vanishing beyond the event horizon. Most of the time, though, the black hole is quiet, dormant, not actively feeding, just sitting there, a gravitational anchor at the galaxy's heart, pulling everything into slow orbits around itself. But evidence suggests it wasn't always quiet. Enormous gamma-ray bubbles extend above and below the galactic center, structures so large they span tens of thousands of light-years. These Fermi bubbles, as they're called, may be remnants of a time when Sagittarius A star flared violently, when it fed aggressively, launching jets of energy that carved these massive structures into space. If the black hole were active today, if it were a quasar blazing with accreting matter, it would outshine every star in the galaxy combined. The Milky Way would look completely different. That era has passed. For now, the heart sleeps. But one day, perhaps, it may wake again. The central region of the galaxy is shaped strangely, not a sphere, but a peanut, or a box, or an X, a three-dimensional structure that bulges in the middle and narrows at the ends. This peanut shape formed from a bar of stars that crosses the galactic center. Over time, this bar buckled vertically, creating the strange geometry we see today. The bar itself rotates. Slowly, over millions of years, it spins, stirring gas toward the center, shaping the inner spiral arms, feeding material gradually toward the black hole. Bars are common in spiral galaxies. They form naturally when stars near the center drift inward, creating a dense, elongated structure along a central axis. Some astronomers think there may be a second, smaller bar hidden inside the first, a bar within a bar, rotating at a different speed, nested like Russian dolls. From Earth, we can't see the galactic center in visible light. Too much dust, too much distance. The core is hidden behind vast clouds that absorb visible wavelengths completely. But infrared light pierces dust, radio waves slip through. X-rays reveal the hot gas around the black hole. In these wavelengths, the center blazes, a crowded, violent, dynamic place. We are fortunate to live far from the core. Near the center, stars are packed densely, radiation is intense, the black hole's gravity warps orbits unpredictably. It's not a place conducive to life. Out here, in the quiet suburbs, we have room, we have stability, we have time. Time for planets to form, for life to emerge, for intelligence to wonder about the galaxy it inhabits. Distance, it turns out, can be a blessing. The invisible web. Between the stars lies the interstellar medium, a thin mixture of gas, dust, plasma, and magnetic fields that fills the space most people think of as empty. This medium is not uniform. It's structured into filaments, bubbles, clouds, shaped by supernova shock waves, stellar winds, and the motion of the galaxy itself. In some regions, the medium is cold and dense, molecular clouds where stars are born. In others, it's hot and diffuse, million-degree plasma heated by stellar explosions. Cosmic rays stream through this medium constantly. High-energy particles, mostly protons, accelerated to near light speed by supernovae or other violent events. These cosmic rays pass through your body every second, thousands of them. Most pass straight through without interacting. Occasionally, one collides with an atom in your cells, causing a tiny flash of radiation. The galaxy also emits neutrinos, ghostly particles produced in nuclear reactions, so weakly interacting they pass through entire planets without slowing down. Trillions of neutrinos pass through your body every second. From the sun, from distant supernovae, from cosmic ray collisions in Earth's atmosphere, you are bathed in them constantly. Yet, you feel nothing. They slip through matter like light through glass, barely noticing the atoms they pass. Detecting neutrinos requires enormous specialized observatories, tanks of ultra-pure water buried deep underground or under ice, waiting for the rare moment when a neutrino strikes an atom hard enough to produce a detectable flash. These particles carry information from places light cannot reach, from the cores of stars, from the hearts of supernovae, from regions too dense or too distant for photons to escape. The Milky Way is also laced with magnetic fields, weak on earthly standards, but influential over galactic distances. These fields thread through the disk, rise into the halo, shape how gas moves, how cosmic rays travel, how the interstellar medium organizes itself. Dust grains align with magnetic fields, polarizing the starlight that passes through them. By studying this polarization, astronomers can map the invisible magnetic structure of the galaxy. It's beautiful, in a way. The galaxy is not just stars and gas, but a magnetic web, a network of invisible forces, shaping everything.
Strange orbits and wayward stars. Not all stars move in neat circles. Some follow elongated ellipses, orbits that carry them high above and below the galactic plane, tilted at odd angles. These unusual orbits are clues. They suggest foreign origins, stars captured from dwarf galaxies that once orbited independently before being absorbed. Some stars are so old they predate the galactic disk itself. They formed when the Milky Way was just a loose cloud of stars and gas, slowly collapsing inward. These halo stars orbit on paths that reflect that early chaos. No spiral structure to guide them, no disk to keep them in line, just gravity and momentum carrying them on ancient trajectories. The Sun's orbit is not fixed forever. Over time, gravitational interactions with massive molecular clouds can nudge it inward or outward, changing its distance from the galactic center. Stars migrate. They drift gradually through the galaxy, their orbits perturbed by gravitational encounters, by the slow reshaping of the disk, by the dance of gravity playing out over billions of years. Some stars are ejected entirely, kicked out of the galaxy by three-body interactions or supernova explosions in binary systems. They reach escape velocity and leave forever. These hypervelocity stars travel alone in intergalactic space. No galaxy to call home, just endless darkness and the light from distant galaxy clusters. Binary star systems can be torn apart by tidal forces near the galactic center. One star is captured, spiraling toward the black hole. The other is flung outward at incredible speed. These disrupted binaries account for many hypervelocity stars, relationships broken by gravity, partnerships dissolved by the black hole's hunger. The galaxy is full of wanderers, stars that don't belong, immigrants from absorbed galaxies, rogues fleeing disrupted systems, orphans following lonely paths through space. Stellar nurseries and death. Stars are born in cold, dark clouds, molecular clouds, vast regions of hydrogen gas and dust, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly pulls material together. Small clumps grow denser. They collapse under their own weight, spinning and heating as they shrink.
Eventually, the pressure and temperature at the core become intense enough for nuclear fusion to ignite. Hydrogen atoms fuse into helium. Light pours outward. A star is born. This process takes millions of years. From the first stirrings of collapse to the moment fusion ignites, the birth of a star is patient, gradual, hidden within its dusty cocoon. Young stars blow away their birth clouds with powerful winds and radiation. Slowly, the nebula clears. The newborn star emerges, glowing, surrounded perhaps by a disk of leftover material that will form planets. Most stars are born not alone, but in clusters, hundreds or thousands of stars forming together from the same collapsing cloud, siblings in light. Over time, these clusters disperse. Gravitational interactions, tidal forces from the galaxy, and random encounters gradually pull stars away. The family scatters across the galaxy. Our sun was likely born in such a cluster 4.5 billion years ago. Somewhere in the Milky Way, the sun's siblings still shine, stars formed from the same cloud, now separated by thousands of light years. Astronomers are searching for these siblings using data from the Gaia spacecraft. By comparing ages, chemical compositions, and orbital paths, they hope to identify the sun's lost family. A few candidates have been found, stars that might share our origin. If confirmed, they would offer clues about conditions in the nebula that birthed our solar system. When massive stars die, they explode, supernovae, events so energetic they briefly outshine entire galaxies, releasing more energy in seconds than the sun will emit over its entire lifetime. These explosions scatter heavy elements into space: iron, gold, carbon, oxygen, all forged in the star's core, now flung outward in a blast wave traveling thousands of kilometers per second. This enriched material mixes with the interstellar medium. It joins molecular clouds. Eventually, it's incorporated into new stars and planets. Every heavy element in your body came from supernovae. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it synthesized in dying stars, scattered across space, gathered here in you. The galaxy recycles matter across generations. Stars live, die, return their material to space. New stars form from enriched gas. This cycle has repeated countless times over billions of years. Without supernovae, there would be no heavy elements, no planets, no chemistry complex enough for life. We exist only because stars before us died violently. Stellar death is not an ending, it's a transformation. The universe making new forms from old materials, endlessly creating, endlessly renewing. The galactic fountain. Above and below the disk, gas rises and falls in a continuous cycle called the galactic fountain. Supernovae and stellar winds heat gas to extreme temperatures. This hot gas expands upward, escaping the dense plane, rising into the halo. As it rises, it cools. Eventually, it condenses and falls back down, raining slowly onto the disk over millions of years. This fountain redistributes heavy elements. Metals forged in stars are carried into the halo, then fall back, enriching the disk with material needed for new stars and planets. The galaxy breathes. It inhales and exhales. Matter cycles between disk and halo in a patient rhythm that has continued for billions of years. Hot gas also escapes through chimneys, channels carved by supernova clusters. Multiple explosions in the same region punch holes through the disk, allowing gas to vent directly into the halo. These chimneys regulate pressure in the interstellar medium. They shape the halo structure. They're part of how the galaxy maintains equilibrium between star formation and gas depletion. Without this cycling, star formation would have ceased long ago. The disk would have run out of gas. The galaxy would be dead, full of old red stars, no young blue giants, no stellar nurseries glowing with promise. The fountain keeps the galaxy alive. It sustains star formation. It ensures that even in middle age, the Milky Way continues creating new lights. Mysteries that remain. We still don't know the exact mass of the Milky Way. Estimates range from 1 trillion to 2 trillion solar masses. The uncertainty comes from dark matter, invisible mass we can only infer indirectly. We don't know if the Milky Way is heavier than Andromeda. Recent evidence suggests it might be, despite appearing smaller and dimmer. Dark matter halos are difficult to weigh. When the two galaxies collide, their relative masses will determine the outcome: a merger between equals or absorption of one by the other. We won't know until it happens. We don't fully understand what triggered the Fermi bubbles. Were they created by a quasar phase of the central black hole or by an intense burst of star formation? The evidence is ambiguous. We don't know why the Milky Way's disk is warped. Gravitational interactions with the Magellanic Clouds? Dark matter? Internal instabilities? Multiple factors probably contribute, but the exact mechanism remains unclear. We can't see the galactic center in visible light. Too much dust, too much distance. We infer its structure from infrared, radio, and X-ray observations, piecing together a picture from wavelengths that penetrate the veil. We don't know if there are other intelligent civilizations in the Milky Way. Despite decades of searching, we've found no signals. Either we're alone, or intelligence is rare, or we're not listening in the right way. The galaxy may contain billions of Earth-like planets. Kepler data suggests that rocky worlds in habitable zones are common. But common doesn't mean life, it just means opportunity. We don't know what dark matter is, one of the greatest mysteries in science, the invisible scaffolding of the universe. We know it's there, we don't know what it's made of. We don't know if our understanding of gravity is correct. Dark matter may be real, or our equations may be wrong. Perhaps gravity behaves differently on galactic scales than we think. Science is filled with uncertainties, unknowns, questions without answers. This is not weakness, this is honesty. This is the frontier, the edge where knowledge meets mystery.
You are here. The atoms in your body were forged in stars. Carbon in your cells, iron in your blood, oxygen in your breath, all created in stellar cores scattered by supernovae, gathered here in you. You are a temporary arrangement of stardust, elements borrowed from the galaxy, assembled briefly into consciousness, destined eventually to return to the cosmic cycle. The Earth beneath you is made of the same material. Rocky planets form from the debris of stellar death: silicon, iron, magnesium, oxygen, all fusion products from previous generations of stars. The sun above you is a third-generation star. It inherited enriched gas from stars that died before it was born. We live in a solar system built from recycled matter. The light from every star you see traveled years or decades or centuries to reach your eyes. You're seeing the past, the galaxy as it was, not as it is. Some stars you see tonight have already died. Their light is still traveling toward you, but the stars themselves are gone, collapsed into white dwarfs, neutron stars, black holes. The Milky Way will outlive the sun. Our star will die in about 5 billion years. The galaxy will continue long after, making new stars, absorbing new satellites, evolving slowly toward collision with Andromeda. Humanity's entire existence is a brief flicker on galactic timescales.
Modern humans have existed for about 300,000 years. The galaxy has existed for 13 billion, 40,000 times longer. Yet, here we are, briefly conscious, briefly wondering, small sparks of awareness flickering in the cosmic dark, looking up, asking questions, finding ourselves part of something larger. The universe is vast, but it is not separate from you. You are made of it. You are it, briefly organized in a way that can think, feel, marvel at its own existence.
Drifting now into sleep. And now, let the facts fade. Let the numbers blur. Let your mind stop grasping, stop trying to remember, stop holding on. You've drifted through 150 truths about the Milky Way. You've heard of stars and dust, black holes and dark matter, collisions and cosmic recycling. But you don't need to remember any of it. These facts were not a test. They were a lullaby, a gentle current to carry you from waking towards sleep. Tonight, as you rest, the galaxy continues turning. Stars are being born in cold clouds. Others are dying in brilliant explosions. Gas rises and falls in the galactic fountain. Satellites orbit and dissolve. The universe breathes in and out. And you are part of it, floating in the Orion spur of a barred spiral galaxy, orbiting a quiet yellow star on a planet that holds just enough water, just enough warmth, just enough stability for something as improbable as consciousness to emerge.
You are here. The atoms in your body were forged in stars, carbon in your cells, iron in your blood, oxygen in your breath, all created in stellar cores scattered by supernovae, gathered here in you. You are a temporary arrangement of stardust, elements borrowed from the galaxy, assembled briefly into consciousness, destined eventually to return to the cosmic cycle. The Earth beneath you is made of the same material. Rocky planets form from the debris of stellar death, silicon, iron, magnesium, oxygen, all fusion products from previous generations of stars. The Sun above you is a third-generation star. It inherited enriched gas from stars that died before it was born. We live in a solar system built from recycled matter. The light from every star you see traveled years or decades or centuries to reach your eyes. You're seeing the past, the galaxy as it was, not as it is. Some stars you see tonight have already died. Their light is still traveling toward you, but the stars themselves are gone, collapsed into white dwarfs, neutron stars, black holes. The Milky Way will outlive the Sun. Our star will die in about 5 billion years. The galaxy will continue long after, making new stars, absorbing new satellites, evolving slowly toward collision with Andromeda. Humanity's entire existence is a brief flicker on galactic timescales. Modern humans have existed for about 300,000 years. The galaxy has existed for 13 billion, 40,000 times longer. Yet, here we are, briefly conscious, briefly wondering, small sparks of awareness flickering in the cosmic dark, looking up, asking questions, finding ourselves part of something larger. The universe is vast, but it is not separate from you. You are made of it. You are it, briefly organized in a way that can think, feel, marvel at its own existence.
Pulsars, cosmic lighthouses. When massive stars collapse, they sometimes form neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons on Earth. Some neutron stars spin, fast, incredibly fast, hundreds of times per second, rotating with a precision that rivals atomic clocks. These spinning neutron stars have powerful magnetic fields. As they rotate, beams of radiation sweep through space like lighthouse beams, pulsing regularly with each rotation. From Earth,
We detect these pulses as pulsars, stars that blink on and off with metronomic regularity. The first pulsar was discovered in 1967, and for a brief moment, astronomers wondered if they detected alien signals. But no, these are natural phenomena. Dead stars spinning in the darkness, their last dance before cooling into invisibility over trillions of years. Pulsars keep extraordinarily accurate time. Some millisecond pulsars are more regular than atomic clocks, pulsing thousands of times per second with deviations smaller than microseconds over decades. Astronomers use pulsars as cosmic GPS systems. By measuring the tiny delays in pulsar signals caused by gravitational waves passing through space, they can detect ripples in space-time itself. The Milky Way contains thousands of known pulsars and probably hundreds of thousands more waiting to be discovered. Each one a remnant of stellar death, spinning silently in the dark, broadcasting its presence to anyone listening. Some pulsars are in binary systems. They orbit other stars, and by measuring how their pulses change as they orbit, astronomers can test Einstein's theory of general relativity with extraordinary precision. One famous pulsar, PSR 1913+16, is slowly spiraling toward its companion star. As it does, it loses energy by emitting gravitational waves, exactly as Einstein predicted. The discovery earned its finders a Nobel Prize. Pulsars remind us that death is not an ending, but a transformation. A star dies, but something remains, spinning, radiating, marking time in the cosmic dark.
The magnetic galaxy. The Milky Way is threaded with magnetic fields. Invisible to human eyes, but influential over immense distances, these fields shape how matter moves through the galaxy. Magnetic fields are created by moving charged particles. In the disk, cosmic rays and ionized gas flow through space, generating fields that align roughly with the spiral arms. These fields are weak compared to Earth's magnetic field. You'd need to measure across light years to detect their strength. But on galactic scales, they're powerful enough to guide the motion of gas clouds and cosmic rays. Interstellar dust grains align with magnetic field lines. As starlight passes through aligned dust, it becomes slightly polarized. By measuring this polarization, astronomers can map the invisible magnetic structure of the galaxy. The magnetic field also rises into the halo, forming loops and arcs that extend thousands of light years above the disk. These structures are shaped by supernova explosions and stellar winds pushing material outward. Cosmic rays follow magnetic field lines. These high-energy particles spiral along the fields, bouncing back and forth between field lines like balls in a pinball machine, taking millions of years to escape the galaxy. Without magnetic fields, cosmic rays would stream directly out into intergalactic space. The fields trap them, keeping them circulating through the galaxy, influencing star formation and heating the interstellar medium. Radio telescopes reveal stunning complexity in the galactic magnetic field. Filaments, bubbles, twisted structures that defy simple explanation. The magnetic landscape of the Milky Way is rich and strange. Understanding these fields is crucial for understanding how galaxies work. They affect star formation, gas dynamics, cosmic ray transport, nearly every process happening in the interstellar medium. Yet magnetic fields remain one of the least understood aspects of galactic astrophysics. We see their effects, we map their structure, but the detailed physics of how they form and evolve is still being worked out.
Globular clusters, ancient spheres. Scattered through the galactic halo are over 150 globular clusters.
dense, spherical collections of hundreds of thousands of stars packed into regions just a few dozen light-years across. These clusters are among the oldest structures in the galaxy. Some are over 12 billion years old, formed when the Milky Way was young, before the disk had fully settled into its current shape. The stars in globular clusters are ancient and metal-poor. They contain very few heavy elements because they formed before many generations of supernovae had enriched the galaxy with metals. Metal-poor stars shine redder and fainter than metal-rich stars of the same mass. This gives globular clusters a characteristic golden color, thousands of old red stars packed together in a glowing sphere. The cores of globular clusters are so densely packed that stellar collisions are possible, rare but real. When stars collide in these crowded environments, they can merge, creating unusual objects called blue stragglers. Blue stragglers appear younger than the other stars in the cluster. They're bluer and more luminous, as if they were recently born. But they're not young, they're rejuvenated, created by collisions or mass transfer in binary systems. Globular clusters orbit the galactic center on long, slow paths that carry them high above and below the disk. They take hundreds of millions of years to complete one orbit. As they pass through the disk, tidal forces from the galaxy's mass gradually strip away their outer stars. Over billions of years, clusters lose members, slowly dissolving into the galactic halo. Some globular clusters may have been captured from dwarf galaxies absorbed by the Milky Way. Their orbits and compositions suggest foreign origins, memories of galaxies that no longer exist. Studying globular clusters helps astronomers understand the early history of the Milky Way. They're like fossils, ancient structures preserved from the galaxy's youth, carrying information about conditions billions of years ago. The most famous globular cluster visible from Earth is Omega Centauri. With nearly 10 million stars, it's so large and massive that some astronomers think it might be the remnant core of a dwarf galaxy that was absorbed long ago.
The habitable zone of the galaxy. Just as planets orbit in habitable zones around their stars, not too hot, not too cold, the galaxy itself may have a habitable zone where conditions favor complex life. Too close to the galactic center and radiation from the supermassive black hole, frequent supernovae and dense star populations would make long-term planetary stability difficult. Too far from the center and metallicity drops. Heavy elements become scarce. Rocky planets are harder to form. The chemistry of life might lack essential ingredients. Somewhere in between lies a galactic Goldilocks zone, a broad ring where stars have enough heavy elements to form planets, but aren't so close to the center that radiation would sterilize worlds. Earth sits within this zone, about 26,000 light-years from the center, not in the inner chaos, not in the outer poverty, but in the comfortable middle where conditions are stable. This doesn't mean life exists only in this zone. Life is adaptable. It might arise in unexpected places. But the galactic habitable zone represents the regions where conditions seem most favorable. The zone isn't static. As the galaxy evolves, metallicity increases everywhere. The habitable zone may expand outward over time as outer regions become enriched with heavy elements from supernovae. When the Milky Way was young, the habitable zone may have been narrow or non-existent. Not enough heavy elements, not enough time for planets to form and cool. Life, if it exists elsewhere, may be relatively young on cosmic timescales. Or perhaps life is ancient. Perhaps it arose in metal-rich pockets even in the early galaxy. Perhaps intelligence has risen and fallen countless times over billions of years, leaving no trace we can detect. We search for signals from other civilizations. We listen with radio telescopes. We look for techno-signatures, evidence of technology altering the galaxy in detectable ways. So far, we've found silence. The Fermi paradox asks, if life is common, where is everyone? The galaxy is ancient and vast. If intelligence arises frequently, we should see evidence, yet we don't. Why? Perhaps life is rare. Perhaps intelligence is rarer still. Perhaps civilizations destroy themselves quickly. Perhaps they transcend physical form and become invisible to us. Perhaps they're hiding. Perhaps they're here and we just don't recognize them. Or perhaps we're alone. Perhaps Earth is a singular miracle. Perhaps consciousness is an accident so unlikely it's happened only once in this entire galaxy of hundreds of billions of stars. We don't know. This is one of the greatest mysteries. Are we alone, or are we one of many? The silence offers no answers, only questions that echo through the dark.
The Milky Way's family. The Milky Way doesn't exist in isolation. It's part of a small cluster called the Local Group, about 50 galaxies bound together by gravity, drifting through space as a family. The two largest members are the Milky Way and Andromeda. Each has their own retinue of smaller satellites, dwarf galaxies that orbit like moons around planets. The Milky Way has dozens of known satellite galaxies. The largest are the Magellanic Clouds, visible from the southern hemisphere as bright smudges separated from the main band of the Milky Way. Other satellites are much fainter, dwarf spheroidals with only millions of stars, barely luminous, detectable only through careful surveys. Some may be among the darkest galaxies in the universe, dominated by dark matter, containing very few stars. These dwarf galaxies are gradually being absorbed. Their stars are stripped away by tidal forces, forming streams that wrap around the Milky Way like ribbons. The Sagittarius dwarf galaxy, discovered in 1994, is being torn apart right now. Its stars form streams that loop around our galaxy, evidence of its slow dissolution. Dwarf galaxies are important for understanding dark matter. Their mass-to-light ratios are extreme. Some appear to be almost entirely dark matter with just a thin frosting of stars. The distribution and orbits of satellite galaxies also test models of galaxy formation. Simulations predict certain patterns. Observations sometimes disagree. These discrepancies drive theoretical refinements. Beyond the Local Group lie other galaxy clusters. The Virgo cluster, containing thousands of galaxies, dominates our corner of the universe. The Local Group is falling toward it, pulled by its collective gravity. On even larger scales, galaxies organize into superclusters and cosmic filaments, the largest structures in the universe, forming a web that spans hundreds of millions of light years. The Milky Way is part of Laniakea, a supercluster containing 100,000 galaxies, all flowing together toward a region called the Great Attractor, pulled by gravity we can measure but cannot fully explain. Cosmic motion is complex. We orbit the Sun. The Sun orbits the galactic center. The Milky Way falls toward Andromeda. The Local Group falls toward Virgo. Virgo flows within Laniakea. Everything moves, nested motions within larger motions, drifting through an expanding universe.
Radio whispers and X-ray fires. The Milky Way speaks in wavelengths beyond human vision: radio, infrared, ultraviolet, X-rays, gamma rays. Each reveals a different aspect of the galaxy's nature. In radio wavelengths, cold hydrogen glows faintly. This gas is everywhere, filling the space between stars, tracing spiral arms, revealing structure hidden by dust in visible light. radio observations mapped the galactic warp. Radio telescopes detected the neutral hydrogen extending far beyond the visible disk, bending upward and downward in graceful curves invisible to optical telescopes. Pulsars broadcast in radio. Their beams sweep through space at radio frequencies, pulsing with clockwork precision, revealing the locations of dead neutron stars scattered through the galaxy. Molecular clouds emit radio waves from molecules like carbon monoxide. By mapping these emissions, astronomers locate stellar nurseries hidden within dark dust clouds. In infrared, the galaxy glows with warmth. Heat heated by starlight re-radiates in infrared wavelengths, revealing hidden regions of star formation and mapping the thermal structure of the galaxy. Infrared telescopes peer through dust to see the galactic center. What's invisible in optical light blazes in infrared, revealing the crowded stellar populations surrounding Sagittarius A star. In X-rays, the galaxy burns with violence. Hot gas, millions of degrees, glows brightly. White dwarfs accreting material from companions. Neutron stars in binary systems. Black holes feeding on infalling gas. The galactic center shines in X-rays. The region around Sagittarius A star glows with hot, ionized gas being torn apart by the black hole's tidal forces before spiraling inward. Supernova remnants glow in X-rays. The expanding shells of hot gas shine brightly, tracing the locations of recent stellar deaths scattered across the disk. In gamma rays, the galaxy reveals its most energetic processes. Pulsars emit gamma rays. Supernova remnants accelerate cosmic rays to extreme energies. The Fermi bubbles glow with gamma ray light from unknown processes at the galactic center. Each wavelength is a different sense, a different way of perceiving the galaxy. Together, they reveal a Milky Way far more complex and dynamic than visible light alone suggests.
The galactic ecosystem. The Milky Way functions like an ecosystem. Matter and energy flow between components. Stars are born, live, die, return their material. Gas circulates. Everything is connected. Star formation depends on available gas. Too little and formation slows. Too much feedback from supernovae and stellar winds, and gas is heated and dispersed, preventing collapse. The balance between these processes regulates how fast the galaxy makes stars. Currently, the Milky Way forms about 2 solar masses worth of stars per year, a modest rate compared to its peak billions of years ago. Supernovae inject energy into the interstellar medium. They heat gas, create bubbles, drive winds that carry material into the halo. This feedback regulates star formation, preventing the galaxy from converting all its gas into stars too quickly. Without feedback, the galaxy would have exhausted its gas supply long ago. All the hydrogen would be locked in stars. The disk would be dead, full of red dwarfs and white dwarfs, no stellar nurseries, no young blue giants. Gas inflows replenish what's lost. Material from the intergalactic medium falls into the galaxy, providing fresh fuel for ongoing star formation. This inflow is mostly cold gas, streams of neutral hydrogen following filaments of the cosmic web, slipping quietly into the disk, adding to the reservoir from which new stars form. This balance between star formation, feedback, and inflow determines the galaxy's evolution. Change one parameter and the entire system responds, adjusting until a new equilibrium is reached. This balance may be delicate. Small changes could trigger starbursts, periods of intense star formation that rapidly consume available gas, or quench star formation entirely, turning the galaxy passive. The Milky Way has maintained a relatively steady state for billions of years, not unchanging, but stable. This stability may be rare,
Many galaxies experienced violent starbursts or sudden quenching. Ours remained calm. This calmness may have been crucial for life. Intense starbursts would flood the galaxy with radiation from supernovae. Quenching would reduce heavy element production, limiting the material available for planets. Moderation, it seems, favors habitability.
Rogue planets and orphaned worlds. Planets don't always remain bound to stars. Some are ejected from their birth systems by gravitational interactions, flung out into the galaxy to wander alone through the dark. These rogue planets, orphaned worlds drifting through interstellar space, are difficult to detect. They emit no light of their own, they reflect no starlight, they're invisible except through rare gravitational lensing events. But statistical estimates suggest they may outnumber stars. For every star in the galaxy, there might be one or more rogue planets wandering the darkness between. Some were never part of planetary systems. They formed directly from collapsing gas clouds, too small to ignite fusion, ejected before they could be captured by a star. Others were ripped away from their parent stars by passing objects. Close encounters with other stars or massive planets can fling smaller worlds into interstellar exile. Once freed, rogue planets cool rapidly. Without a star's warmth, their surfaces freeze. Any atmospheres might collapse into ice. They become cold, dark, silent worlds, drifting through eternal night. But some might retain internal heat. Planets massive enough may have molten cores kept warm by radioactive decay. Beneath frozen surfaces, subsurface oceans might persist for billions of years. Could life exist on rogue planets? It seems unlikely, but not impossible. Hydrothermal vents on Earth support ecosystems without sunlight. Perhaps similar environments could exist beneath the ice of rogue worlds. The Milky Way's halo may be filled with rogue planets, billions of them perhaps, scattered through the vast empty spaces, invisible orphans of galactic dynamics. Some might even pass through our solar system occasionally. Small, dark, fast-moving, they'd be nearly impossible to detect unless they passed very close. These wandering worlds remind us that planetary systems are not permanent. Stability is temporary. Orbits can be disrupted. Worlds can be lost. The galaxy is full of exiles.
Time and transformation. Nothing in the galaxy is permanent. Everything changes, though often too slowly for human timescales to perceive. The spiral arms shift position over tens of millions of years. The pattern drifts, warps, reforms in response to gravitational perturbations and gas dynamics. The bar at the galactic center rotates, completing one rotation every few 100 million years. Its orientation changes slowly, influencing the inner spiral structure. The galactic warp precesses. The direction of the bending changes over time, rotating like a wobbling plate spinning slowly through space. Star formation rates fluctuate, sometimes higher, sometimes lower, responding to available gas, recent mergers, passages through the spiral arms. The black hole at the center alternates between active and dormant phases, long periods of quiet punctuated by brief flares when material falls inward. Over billions of years, the galaxy's morphology evolves. What was once a pure spiral may develop a bar. What was barred may lose its bar. Structure forms and dissolves. The Milky Way of today is not the galaxy of 10 billion years ago. It was smaller then, less massive, perhaps with different spiral structure, certainly with fewer heavy elements. And the galaxy 10 billion years from now will be different still, merged with Andromeda, possibly with other local group members, transformed into something new. Change is the only constant. The universe is not static, but dynamic. Everything evolves. Stars,
galaxies, clusters. Even the fabric of space-time itself expands, carrying galaxies apart. This impermanence is not sad, it's beautiful. The universe is creative, always making new forms, always transforming, always becoming.
Welcome, weary traveler. Welcome to Science for Sleep. Tonight, you have nowhere to be, nothing to do but rest. Let the tension dissolve from your shoulders like morning mist under sunlight. Let your breathing slow, your thoughts soften, your body remember the art of stillness. We're about to drift through 150 quiet truths about the Milky Way, whispered facts, cosmic secrets, gentle revelations. You don't need to remember them all. You don't need to hear every word. These truths are here simply to carry you, like a current carrying a leaf, gently downstream into sleep. If these peaceful explorations help you find rest, consider liking, subscribing, or sharing with another soul who struggles to quiet their mind. But for now, let everything fall away. Close your eyes if you wish. Settle deeper and let the galaxy sing you to sleep. Let's begin.
The view from inside. We see the Milky Way edge on because we're inside it. The pale band across the night sky is our view along the disk, looking through the thickness of the galactic plane. If we could see the galaxy from outside, from above or below, it would look like a majestic spiral, bright core, graceful arms, obvious structure. From Earth, we see only a ribbon, a river of stars compressed by perspective into a narrow band stretching horizon to horizon. The galactic center lies in the direction of Sagittarius. On dark nights away from cities, this region appears brighter, more crowded, glowing with the overlapping light of billions of stars. The opposite direction, toward the outer reaches of the galaxy, appears sparser, fewer stars, less light. We're looking toward the edge, where the disk thins and star density drops. This inside view limits what we can observe. Dust obscures large portions of the disk. Distance makes faint objects invisible. We piece together the galaxy's structure from fragmentary glimpses. It's like trying to understand a city while standing at street level. You see buildings around you, you infer overall layout, but you can't see the whole pattern without stepping back. Astronomers overcome this by combining many observations, distances to star clusters, velocities of hydrogen clouds, distribution of molecular gas, positions of young stars. Each adds pieces to the puzzle. Gaia, the spacecraft mapping over 1 billion stars, has revolutionized our understanding. By measuring precise positions and motions, Gaia reveals the three-dimensional structure and dynamics of the galaxy. Still, mysteries remain: the exact spiral structure, the total mass, the distribution of dark matter, the history of mergers, the future evolution. We're making progress. Each decade brings new instruments, new data, new understanding. But the Milky Way guards its secrets well, revealed slowly to patient observers.
Gravitational waves through the galaxy. Space-time itself ripples with gravitational waves, distortions caused by accelerating masses, traveling at light speed through the fabric of reality. Major sources include merging black holes, colliding neutron stars, and binary systems where massive objects orbit closely. These events send ripples radiating outward, stretching and compressing space as they pass. Gravitational waves pass through the Milky Way constantly. Most are incredibly faint, created by events in distant galaxies, weakened by distance until they're nearly undetectable.
But occasionally, something nearby creates strong waves. In 2017, two neutron stars merged in a galaxy 130 million light-years away. The waves reached Earth along with light from the explosion. Ground-based detectors like LIGO can detect these waves. Massive interferometers measure how passing waves minutely stretch and compress the space between mirrors suspended kilometers apart. The detection of gravitational waves confirms Einstein's predictions. It opens a new way of observing the universe, not with light, but with ripples in space-time itself. Astronomers are building even more sensitive detectors. Space-based interferometers will detect lower frequency waves from supermassive black hole mergers. Pulsar timing arrays will detect ultra-low frequency waves that ripple through the galaxy. The gravitational wave background, a faint hum from countless mergers throughout cosmic history, may be detectable soon. This would reveal the statistical properties of black hole populations across the universe. Every major astronomical breakthrough opened new windows on the universe. Telescopes, photography, radio astronomy, X-ray satellites. Now, gravitational wave astronomy adds another sense, another way of perceiving cosmic events. What we'll discover is unknown. That's the beauty of new tools. They always reveal surprises, phenomena we didn't predict, objects we didn't know existed, physics we didn't fully understand.
The sleeping heart. And now, let your mind quiet. Let these facts dissolve like sugar in water, sweetening your thoughts but leaving no solid residue. You've wandered through 150 truths, listened to whispers of spirals and dark matter, pulsars and orphaned worlds, ancient mergers and future collisions. The galaxy continues without your attention. Stars form in cold clouds, supernovae scatter heavy elements, pulsars spin in darkness. The black hole sleeps at the center, dreaming perhaps of ancient fires. Gas rises and falls in the galactic fountain. Planets orbit their suns. Cosmic rays spiral through magnetic fields. Neutrinos pass through everything like ghosts through walls. And here you are, a temporary arrangement of stardust, briefly organized into consciousness, resting on a rocky planet in a quiet corner of a barred spiral galaxy. The iron in your blood was forged in the core of a massive star that exploded before the sun was born. The calcium in your bones came from a supernova billions of years ago. The oxygen you breathe was created in a different star entirely, then scattered across space and gathered here. You are recycled starlight, cosmic dust briefly aware of itself, a way for the universe to know itself, to look back at its own history, to wonder about its own nature. Tonight, as you drift towards sleep, the galaxy drifts too, moving through space at 600 kilometers per second, orbiting the galactic center in its patient 225 million-year loop, slowly approaching Andromeda for a collision billions of years away. Everything is moving. Everything is changing. Everything is temporary, including you, including Earth, including the Sun, including the Milky Way itself. But temporary doesn't mean meaningless. Brief doesn't mean insignificant. You are here now, conscious now, wondering now, and that is enough. Let the stars watch over you. Let the galaxy carry you through space. Let the universe cradle you in its immense, patient arms. If you're still awake, that's fine. The next video will begin shortly. But most likely, you're already gone, already drifting, already dreaming. Sleep well, traveler. Dream softly among the stars. The galaxy will still be here when you wake. Good night.
Collisions in slow motion. The Milky Way has absorbed dozens of smaller galaxies throughout its history. We are not pure, we are composite, built from galactic cannibalism, stitched together from the wreckage of worlds that wandered too close. Right now, at this very moment, the Sagittarius dwarf galaxy is being torn apart by our gravity. Its stars are being pulled into long streams that wrap around our disk like ribbons. We are eating it slowly over millions of years. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. Two spirals approaching each other at hundreds of kilometers per second, growing closer with every passing moment. The collision will not be violent in the way you might imagine. Stars are spaced so far apart that direct impacts are almost impossible. But gravity will warp both galaxies beyond recognition. Tidal forces will stretch both spirals into long, sweeping arcs. Arms will curl outward into space. The shapes we know will blur, fold, merge over billions of years into something neither galaxy has been before. After the merger, the combined galaxy will likely be an elliptical, no longer a spiral, but a vast, aging sphere of stars. No more spiral arms, no more structure, just a golden cloud of ancient light. Some stars will be flung outward during the collision, ejected into intergalactic space, rogue suns wandering the void between galaxies, forever alone. The supermassive black holes at each galaxy's center will spiral toward each other. Eventually, they too will merge, creating gravitational waves that ripple across the universe. By the time this collision happens, Earth's sun will already be dying. The merger of galaxies will unfold as our own solar system faces its end. Two cosmic events, two endings, happening together. But new stars will be born from the collision. Gas clouds compressed by gravitational chaos will collapse into stellar nurseries. Death and birth, destruction and creation, happening simultaneously across millions of years.